Hi everybody, welcome back. So we've been talking about the analog of our translational motion quantities, velocity, acceleration, kinetic energy, and to our rotational values. So angular velocity, angular acceleration, rotational kinetic energy. One of the things we haven't talked about yet though is the rotational analog of mass. And you might think, well, mass is mass. What difference is it going to make? But if you think about it, it makes a big difference how that mass is distributed. So one of the big things that we need to work on is to define a term that will not only describe how much mass I have, but how it's distributed. Because if I'm going to rotate, we're going to see that it's going to make a big difference how that's done. So as we're going through this, there's going to be a lot of calculus. We're going to have to do a lot of integrations in order to find that moment of inertia, which is what we call it. So just remember, it's really a straightforward process, even if there are a lot of integration steps to get you there. Let's get started. All right, so as we mentioned, it's going to be more than just the amount of mass, it's going to be how that mass is distributed. And one of the best ways to see that is to take like a barbell. So here we've got our crude little barbell, and we've got the same amount of mass on either side. So if we were to throw it in the air, for example, where is it going to rotate? Well, it's going to rotate around its center of mass. That's where I've got the same amount of mass on one side as I have on the other. That's our definition of our center of mass. So in this case, then, that's going to be right here. Because I've got this, the body is symmetric, and so it's going to have just as much mass on this side as I have on the right side over here. All right, so if we're going to spin it then, it's going to rotate around that center of mass. And that just kind of makes sense if you think about it, right? You take it, it's going to spin. You're not going to be able to throw it and spin it in such a way that it's kind of lopsided like that. No matter what you do, even if you try to push that outside one harder, it's still going to rotate around its center of mass. All right, so look on the next page then. What if we now have an asymmetrical object? So we've taken off one of the heavy barbell weights and we've put on a smaller one on here. So where is the center of mass going to be in this case? And remember, the center of mass is where I have the same amount of one on one side of that point as I have on the other. Pause the video, think about it, and let's draw that in. All right, so now you should be able to see that I've got more mass on the left side than I do on the right side, at least of the center. So that means my center of mass then must be shifted to somewhere back here. See if that makes sense. Another way you can think of the center of mass, and the reason why we write it with this little triangle, this fulcrum, is if this were like a seesaw, a teeter-totter, then if I balance it on that point, then my object will be perfectly straight. It won't try to fall this way, and it won't try to fall this way. If I were to try to balance this object in the center, let's switch to red here. What if I were to try to balance it right here? What's going to happen? Well, then this is going to move down and this is going to move up, and so it's going to rotate in that case. So as long as I have my support point at that center of mass, then it's going to stay straight. It's not going to rotate at all. So the question then, let's look at this and make sure we understand our terminology. Which would be easier for it to rotate quickly around the center of the mass? Either our lopsided barbell or our symmetric barbell? Which one's going to be easier to rotate around that object's center of mass? Well, it's a little bit of a trick question, right? It's going to be the same. Each one wants to rotate around its center of mass. And so no matter what I do, if I take that lopsided barbell, it's going to do this because it's rotating around its center of mass from there. So it requires the same amount of effort to rotate around the center of mass, but where that center of mass is will change. This next one is going to be something for you to think about then. So what if we rotated the unequal weight around the same axis as we did in the first one? So let me go back to my red. So let's say that we're rotating it right here. Okay. Which one is going to rotate more easily, the equal one or this lopsided one? So it's fixed here and I'm trying to spin it. Well, it's the equal weight one is going to be much easier, right? Because it's going to naturally spin about this. So even if this thing is sitting on the ground like this, whereas we'll copy my equal weight barbell over here, and I'm suspending them in the same point. And I want to try to make it rotate this way. And I'm going to try to make this one rotate this way. So the equal weight barbell is going to spin very easily, right? It's going to, because it naturally wants to spin around that always wants to spin around the center of mass. This one, though, wants to spin right here, and we're not letting it. We've attached it to this fulcrum right here. And so it's going to be harder for me to get that to spin in a regular way. And so the equal weight barbell is going to be the easier one to rotate quickly. Okay, so this ease of rotation then is what we call the moment of inertia. If you think about what you've heard about with inertia up to this point, you know, maybe I've got a block and I'm pushing it this way. Well, we say that it's going to take more force. So if this is the velocity I'm getting, it's going to take more force the more mass I have. And that's been described as saying, well, the block here has more inertia. And so we need more force to overcome that. And we mentioned this before, but in fact, there is no experiment you can do that will distinguish inertia from mass. Inertia is mass, and mass is inertia. There are two names for exactly the same thing. If I increase my mass here, it's going to require more force. So you can use those terms interchangeably. The moment of inertia, a moment just means that it's being applied at some distance. So let's say that this is my center point that I'm going to be measuring from. So now I've got a mass out here at some distance r. So that's our moment. And a moment is a torque, which we'll talk about in our next section. But basically, the idea of a moment is not anything to do with time. It's about how far away from this axis of rotation I am. So in this case, what we're talking about then is the distribution of mass. So there are three factors that are going to determine how easy it is for it to rotate. And remember, that's the same analogy that we have here. The only thing that determined how easy it was for me to push it was its inertia, which was its mass. In this case, there are three things that's going to determine how easy it is for me to get it to rotate. First is going to be the mass of the object. That's the way it was before. Something that's heavier, even if I have two equally distributed barbells, right? If these two weights are less than these two weights, it's going to be easier for me to spin the lighter weight. Should make sense there. So the greater the mass, the harder it's going to be. That's kind of inertia in its normal sense that you're used to thinking about it up to this point. But this is what's new. The distribution of the mass also matters. And so we see that with our unequal weight barbell. So it's going to, if I've got this unequal weight, then it's going to be harder for me to rotate around it. And then that leads to this last one that tells me that the location of the axis of rotation is also going to make a difference. If I try to force it to rotate in the middle, that's going to be harder than if I put my fulcrum directly underneath that center of mass. So when we're looking at an actual object, be that a robot or anything else that we're looking at, we can no longer consider it to be a point mass that's turning or rotating. So, you know, up to this point, we may have drawn our robot going like this, right? But we actually considered all of the force to be right here in the center of mass as it was rotating around. And that's actually not the case, because now if I want that thing to rotate, then it depends upon how the mass of the robot is distributed as well. And so to keep things simple, we're going to rotate it around just one axis. So I could rotate my robot. I could put that robot so that it's on its center of mass, and so it's rotating this way. So maybe these are my wheels. And I could do any kind of shape that I want, but you should see that, you know, having all the mass on the outside is going to be a lot different than having the mass concentrated here in the middle. Okay, so this brings us to this idea of how can we calculate it. Well, let's start with a little bit simpler shape than just our full robot here. So instead, let's look at the tires. We want these wheels, so here's my robot wheel, and we're going to say that it's fairly thin, like this, and it's going to be a solid disc that's rotating around that axis. Okay, so we probably want it to be pretty easy for it to rotate. That means that the motors will have an easier time getting to rotate, or conversely, I can get more rotation out of the same amount of force of the motor. Well, that's obviously a good thing. That's something that we want. So we need to know what is that moment of inertia for this particular shape. Turn over to the next page. All right, so here's our wheel, and we're rotating around this axis here. And we want to figure out what is the moment of inertia for this. Well, we're rotating with this angle omega here. Make that a little bigger so you can see it. We're going to say that the wheel has a radius of r, and then I'm going to have to integrate over the entire outer radius. Let me draw this flat so that we can see it. So you should see that I get a different moment of inertia for these pieces that are rotating very close to the axis than I do for these pieces that are rotating farther out. That's kind of the analog of having in close, I've got, this same weight barbell, versus having it having everything distributed. Let me draw another example, see if this makes sense. So here I'm going to work with a single barbell. If I've got it attached here and I try to rotate, right, I'm way away from the center here that I'm trying to rotate for that. On the other hand, if I attach my barbell right here, now I'm much closer to the center of mass. And so this is going to rotate around much more easily than this one will. Okay? So what we're leading up to there is that where I am on the wheel, on the disc in this case, is going to change how much effort I need to overcome its inertia, its moment of inertia in this case. Well, that means since it's changing with the radius away from the center of the wheel here, then that means I've got no choice, but I've got to integrate this. So I can take any tiny little piece of the mass here, right? And then I'm going to integrate from r over here to dr. So this little piece of mass here then has a radius of dr. Okay. All right. So let's write down the expression for kinetic energy for this little piece of mass right here. Now we're going to write down the translational kinetic energy. So you see that instantaneously it's moving in this direction, and that's our along track velocity, our tangential velocity that we talked about before. So using the tangential velocity, pause the video and write down the expression for the translational kinetic energy, how it's moving straight forward at that very instant. All right, well, this is just our regular kinetic energy, so we know EK, and I'm going to put T so that I make sure that we're talking about the same thing here, is going to be 1/2 times the mass times VT squared. Right? Now, that's our general expression. However, our mass in this case is only this tiny little piece dm. So my kinetic energy for just that tiny little piece must be dm, and I'm going to drop the t just to save myself from quite so many subscripts. So I'm going to put this in parentheses so we don't think d and m are two different symbols. So this is dm, that tiny little piece. All right, the velocity is the tangential velocity. All right, now we want to write down an expression for the tangential velocity. Well, go back to when we first started talking about rotational kinematics. Remember that we know that we are rotating around the wheel this way with an angular momentum. I'm sorry, with an angular velocity here of omega. So how do I translate that omega into our tangential velocity? And if you need to go back through your notes, you can. Pause the video and see if you can find it. You should have gotten that Vt is equal to omega times r, where r is the distance away from the center that I'm trying to rotate. So my tangential velocity at this point is simply going to be omega times r. All right, so let's take that and let's plug that into our kinetic energy expression. So we can do that right here. So our translational kinetic energy then is going to be 1/2. We're going to use this form here, times dm, and then times omega r, but then that whole thing has to be squared. Okay? All right, so if I'm going to, let's simplify. So the next thing I want to do is I want to see how this relates to my rotational kinetic energy. because in reality, this thing is actually rotating rather than translating. But energy is energy. So the energy that it has, if it would have been translating, so if I had suddenly, whirling that string over my head, if I finally release that string, then its translational energy, kinetic energy, must equal its rotational kinetic energy, right? Because conservation of energy. So how do you think an expression for the rotational kinetic energy might look? So this is my general expression for my translational kinetic energy. What might the rotational kinetic energy look like? And the way we do this is we substitute in our symbols using our little cheat sheet that we had when we were first deriving our kinematics equations. So the 1/2 obviously stays the same. M now, the analog of the mass in the translational case, is going to be the moment of inertia, which we use a symbol I for. Now you may say, oh, wait a minute, isn't that going to be my impulse? Well, yes, we're basically running out of symbols. However, notice that I is not a vector in this case. But later on, we're actually going to use I for the intensity of the light that we're going to be looking at. So we're going to reuse symbols. Remember that doesn't matter. You could call that smiley face, and it's not going to change what the symbol actually is. It is the moment of inertia, and physical reality doesn't matter what you call it. So we'll use this symbol, and so I is going to be equal to our moment of inertia. And again, you can think of that as being like the mass, but it also includes how the mass is distributed. All right, and then our analog of the velocity is omega squared, like that. All right, so now here's where the trick comes in. We need to massage this so that it's got the same form as our kinetic energy, and actually we're going to be using this form for the kinetic energy. So we want to take our translational kinetic energy, which is this one, remember, and we want to rearrange it so that it's something in this format, so that I can talk about its rotational kinetic energy. All right, see if you can do that. Pause the video and see how can I arrange this so that I get a 1/2 and I get an omega squared, and then everything else that's left is going to be my I. So use this expression right here and see what you can do. Pause the video. All right, well, let's see what we have here. So we know that our kinetic energy, which is now about to be our rotational kinetic energy, remember, all of that translational energy is the same thing as its kinetic energy. And you can prove that because if I were able to let it go, my rotational kinetic energy would 100% be transferred into my translational kinetic energy. All right, so the 1/2 is easy. If I square both of these, then let's just do this step at a time. So I've got a dm, and then I'm going to have an omega squared and an r squared. All right, so let's rearrange things so that we can get it into the form that we want. And so I have EKR is equal to 1/2 times dm times r, let me put that in brackets, times omega squared. Oops, we need r squared here. Forgot my square point term there. Okay, so you see what I've done is I've really just rearranged my expression that I have here in such a way that I can pull this out. Well, then this must be I. So you see that I've got a 1/2, some quantity times omega squared, but I know by definition my rotational kinetic energy is 1/2 I omega squared. So this is going to be my moment of inertia. Now notice though that I don't have the mass, I have this infinitesimal little piece of mass here. So technically I have a dI from that. So let's go ahead let me go ahead and write this out before we go to the next page. So this is actually going to be 1/2 dI omega squared. And so I have then that dI is going to be equal to dm r squared. And if nobody objects, I'm going to put my r squared in front just so that I can stop having to draw my parenthesis around here. And you're used to seeing the dm part being on the end here. All right, let's transfer this over to the next page. So here we've decided then that our dI is going to equal r squared dm. Okay. So to find the moment of inertia then, all I need to do is to integrate over that entire circle. I'm going to keep my wheel on the side here so that we can see it a little bit better. We can do better than that. And so this is my three-dimensional wheel here. This is our center of rotation, so that's our axis coming in like this. Let's draw that in red. And so that's what we're rotating around. All right, and so I'm interested in the moment of inertia of this little piece right there. Okay, so that's the DI that I'm looking for. It's not just the mass. Remember, this little square, this little cube here does have mass. It's got mass dm, but it also matters how far away from the center of rotation that it actually is. All right, so if we want to figure out what is our moment of inertia, then all we need to do is to integrate this expression. So if I have di equals r squared dm, then I'm just going to integrate this. And that's going to tell me what's happening. All right. Now, one thing just to give you a little highlight of what's coming. What's changing is not the amount of mass. What's changing is my distance. So somehow I'm going to have to express this in terms of r. So here we're going to outline kind of what we're looking for. And this is the path that we're going to take anytime that we want to find that moment of inertia. And we pointed out right here, the key is to get our dm in terms of dr, because I'm going to integrate from 0 to capital R, my total radius. Do you see that if I take the little piece of mass here, and then all the way around, and then this little piece, and this little piece, and this little piece, and this little piece, now I will have the entire moment of inertia for the entire object. Well, so since it's r that's changing, I have to find some way to get my dm into a dr so that I can integrate it up here. And that usually is the trick. That's usually what you're going to spend most of the time doing when you're trying to figure out how to find the moment of inertia. So here's the general procedure for what we're going to do. And take a look at our 3 steps here. This is probably worth putting in your flip book so that you kind of remember what to do. So we're going to use the density to get our dr, because remember that the density depends upon the size of this little piece here. And so that gives us one nice relationship between the mass and this dr. This little piece has size dr here. Okay, so we're going to get dm. In this case, it's going to be in terms of dA instead of dV. Now remember, this is actually a solid wheel, and so really I've got something that looks like this. That's my little dm. And so this then has a density times a volume, and that would be dV. What we're going to work with first is, now let's assume that I have a very, very thin disk. And so if this is the thickness of the disk, which we'll call lowercase t, what we're saying is that r is much greater than t, our thickness, not time. We're also running out of symbols there too. So if that's true, then I can consider this to be an infinitely thin disk, right? The error I make is by definition going to be very small. We'll look at the case where this condition doesn't hold in just a minute. But so that means then I don't have to worry about all of this, and instead all of my mass is concentrated just on the surface here. So it's got no thickness here. So this is my dm, but now I'm going to have a small area rather than a volume. And we're just doing this for this demonstration because it's a little bit easier to follow. But you absolutely can do this with a volume instead of an area, and hopefully you'll follow the same pattern a little bit and do that. Okay, so we're going to use our density to get an expression for dm, either in terms of this dA, if I have something really thin, or in terms of dV, if I have an actual thick object that I want to follow. All right, so our normal expression then, we're going to take the derivative of both sides of that volume, and then or the area, and that's going to give me my relationship between dm and dr. We'll show you how that works in just a minute. Once we've got that, then we're going to plug that in, take the derivative of both sides, and we're going to plug that into our expression for dm, and we'll be left with an expression for dr that we can then integrate and figure out what the total I is. All right, so the easiest way to see this is simply to do it. So let's take a look here. Notice we've got this warning here at the top. In order to use this procedure, we're going to integrate over just one coordinate. for what we're doing here. And just to remind ourselves, here's my disk, and now it's an infinitely thin disk. Here's my axis of rotation, and we're rotating this way, right? And I'm looking at little pieces of mass that I'm moving as I move out. So I'm integrating from 0 to r in that case. So I've got this little ring of mass that I'm adding up all the way around. So that ring of mass is going to be right there. I want to look for symmetry. If I've got something that's really blobby, like this, where the density is changing in all these different locations, that's going to be very hard to integrate. We're going to find some techniques then that will help us integrate something like that in just a minute. All right, let's go through this one to start off with. So step one, we need to find a relationship between the density and the mass. Now for an area density, we use this little symbol. This is a lowercase Greek letter sigma. For a volume density, we use this lowercase Greek letter rho. And I can actually probably draw that a little bit better, but it looks like that. So this one is probably the one you're most familiar with. This is equal to the mass divided by the volume. So that gives me my density. This is almost the same thing, it's just it's the mass divided by the area in that case. So one is a surface density and the other is a volume density. Since our disk, we're assuming, doesn't have any thickness, so, or is at least very small compared to our capital R, then we can use our area density. So let's write that down here. So my area density, we use the symbol this sigma, and then that equals m over a. All right, so we want to solve this expression for m, because remember, we're going to need to get a dm. So we're going to solve it for m, and then we're going to take the derivative. Let's do that in multiple steps. So I get sigma times a must equal m. Now I want to take the derivative of both sides, and I'm going to get d, for now we'll leave this in here like this, is equal to dm. So we're almost there. Now we're assuming that this is a uniform disk. We're assuming that the density doesn't change throughout this. Why might I want to do that? Because then I can pull my sigma, my density, outside of my differential. It's not a problem if it's not. I just need to have some sort of equation for how that density varies as I move outward. You know, maybe it's linear, maybe it's quadratic, some way I need to know how my density changes as I move through this disk. Because then I would just be able to, this is going to depend upon R, my sigma here is just going to depend upon R, and I'll be able to take the integral just as I normally would be. But for now, for this demonstration, we're going to assume that I have a uniform disk, that the disk is just made out of the same stuff all the way through. And that's not an unreasonable thing to assume. So I can pull my sigma outside, and so I get sigma dA is equal to dm. Okay, and that's nothing more than just taking the derivative of both sides. Okay, so the next step then says we want to find a relationship between the area, or the volume, it's going to be the area in this case because we've got a surface area, and r, again, or whatever coordinates that we're using. So what is how can I write the area of this disk related to r? What is the area of the circle? What is the formula for the area of a circle? Right? Well, the area of a circle is going to be pi r squared. However, that would be for the entire disk. I only have this little bitty ring here, this m that's gone, this dm that's gone all the way around. So I only have this little bitty ring here. So I'm going to write that then as dA and d pi r squared, like so. So I'm going to take the derivative of both sides so that I get my dA. And that's the area of the ring that gets traced out by this little piece of mass that's going around. And of course I have all the rest of these pieces that gives me my total mass of that ring. Okay, so my pi is obviously a constant. And so that gives me d of r squared, which then is dA is simply 2 pi r dr. Let me spread that out a little bit so we can read it. So it's 2 pi r, that's the derivative of r squared is 2r, and then I have to take the derivative of what's inside, which is then just going to be dr. All right. Okay, so now we're going to take that then. Now that I finally have my dA, I'm going to plug that back into my expression here. Because what I want then is, I want my dm to be a function of dr. And you see how I've accomplished that? This is a technique you're going to use pretty much every time. The relationship between the mass and the radius, if it's got circular symmetry like we have here, is always going to be related to either the area or the volume of the shape there. Okay, so let's put that back in, and so I get sigma, let's put my 2 pi's over here. My sigma 2 pi is going to, oh oops, I need the rest of my terms. My sigma 2 pi, and then I need an rdr, must be equal to dm. And that's the hard part, because everything else was not a differential, right? When we go back to our original expression, which we'll do here in just a minute. So all I needed to know was what was dm with respect to dr. Once I have that relationship, then now I can integrate from 0 all the way out to r. All right? Now I want to take one little aside here. We've originally started out by talking about just this one little piece, but now we've used the entire bit for this ring then that I've formed. And not only is there mass here, but there's mass all the way through this, right? And so this now is the dm that we're talking about. One way you can think about this is we could have taken just this one little piece, and then before we integrated with respect to r, we could integrate it all the way around with respect to theta. And since it's got constant density, taking that all the way around then is just going to give me the mass of that one little ring. So that's effectively what we've done, is we've done an integral with respect to theta, and now we're going to do that integral with respect to r. Okay, so if you don't see that the mass of this should be the mass of the ring, think about it that way, that this is my entire mass of the ring, because I've integrated that little dm all the way around my 2 pi in order to get my total mass there. All right. Okay, so now we're ready to go. The hard part is done. Let's look over on the next page. Okay, so now we're going to put that into our moment of inertia expression. And so remember, just to remind ourselves what we had, it was the integral of di, which is going to give us our I, is going to equal the integral of r squared dm. Okay. And then that means the integral of di is just I. And then now I'm going to take my expression that I just found for dm, and I'm going to put it in here. And so I have r squared times sigma 2 pi r dr. So far, so good. All right, let's clean this up. Let's bring out what we can. Remember that the sigma we assumed was constant because it's uniform density. 2 and pi are obviously constants. So I get I is equal to 2 pi, or 2 sigma, let's write it as 2 pi sigma, just because we're used to saying 2 pi, as 2 pi sigma times the integral of r cubed dr. And that should be an integral that you can do without any real problem. Now remember our limits of integration. We are integrating from 0 to r, to capital R. It's important that we have this. This cannot be an indefinite integral. It has to be a definite integral because this I is a quantity, it's a number. So I have to integrate from 0 to I. And that, just a reminder, that's integrating from 0 all the way out to my capital R. This is my little dr that I'm moving along my path there. All right, so let's take the integral of that. And so I is equal to 2 pi sigma. The integral of r cubed is going to be 1/4 times r to the 4th, right? Evaluated from 0 to r. Well, that we can pull our constants out here then, and so that's going to give me a 1/2 pi sigma, and then r to the 4th minus 0. So let's get rid of our 0 here, and so this is my expression for my final moment of inertia. And that works, and that's perfectly fine. So, however, most of the time though, in engineering, you're not going to be given the density of the material. You're going to be given the mass of the material. If I am given the density of the material, I'm done. I'm ready to go. However, what if I am given the mass? Well, all right then, we need to figure out how I can get there with that. Well, that's just using our definition for this. So our theta then, our sigma, we remember was equal to m over a. So we need to know the area of this entire circle, that way I can get the total mass of that circle. So because the sigma is just going to be m over a. So I need to fill in my a here. So what's the expression for the area of a circle? Well, hopefully you remember this from geometry, but it's just going to be pi r squared. And in this case, though, it's going to be capital R, right? Because I need the area all the way out to the edge. So I want the area all the way here, the area of the entire disk. So if I have sigma and I multiply it by the area of the disk, then that's going to give me my total mass. All right, so putting this in then, that tells me that sigma must be equal to m over pi capital R squared. All right, let's plug this into our expression here, and we're going to see a lot of stuff cancels out. And so I get I is equal to 1/2 pi r to the 4th divided by m, whoops, nope, we need to erase that. There we go. So the sigma's in the top, so I'm going to have an m up here as well. And then this is going to be my pi r squared. You see my pi's cancel, 2 of my r's cancel, and so my final result then is that I is equal to 1/2, I'll use m to represent the total mass, times r squared. And this is the moment of inertia for a thin, uniform disk with that. Now, here's a pro tip. Notice that the units, let's figure out the units of the moment of inertia here. Remember, we can take any equation, we can figure that out. So pause the video, tell me the units for the moment of inertia. Well, it should be pretty easy. It's just going to be kilogram times meter squared. So our moment of inertia has to have kilograms per meter squared. Now, almost every expression that you derive is going to have something times mr squared. It's going to have some number, some c, times mr squared. In this case, it's 1/2. In other cases, it might be 1/12, or it might be 2/3, or whatever. But there's usually going to be some constant times this mr, because that's what's going to make my units work out. So this c, this constant here, is called the shape factor. And I can have 2 different objects that will their moment of inertia will only differ by their shape factor. And so that can help me predict how that new object is going to behave. All right, see if that makes sense to you. Pause the video, go back through it, and see if you can follow all the steps. There's a lot of integration that went into that, but none of it was terribly hard, but there were a lot of steps, a lot of converting from DMs to DRs and things like that that you needed to follow. So make sure that you do that, and then let's try a little bit more complicated case. Okay, so what if then I've got some other shape, right? Maybe the density isn't constant. Well, if the density isn't constant, like we said, then my omega, or my sigma here, is just going to be a function of r. You know, maybe it equals some constant times r to the 1/3 or something really weird like that. That's okay. It's just, instead of pulling this out, I'm just going to substitute that whole thing in there. I'll pull out my theta c, my sigma c, and I'll just have this extra r to the 1/3 inside my integral. So there's no real difference with that. If I give you a surface density that varies with r, it shouldn't slow you down at all. You just figure out, instead of pulling it outside, you're going to plug this into our integral. All right, now up to this point, we've been doing things with spherical symmetry, or cylindrical symmetry technically. So I was able to rotate and only had to integrate around from 0 to r. What if I have something that is not spherically symmetric? So like your robot itself. Your robot, its main board, is going to be a rectangle. And if the robot's going to rotate around that center of mass, let's say that that's the center of mass right here, I need to figure out what is the moment of inertia from that. And so this then, I'm going to look at one tiny little piece right here. And this time I'm not going to bring it around any kind of a ring because I don't have that symmetry that I can do that. So that means by definition, I'm going to have to do both the integrals this time. Before, remember, we integrated effectively over d theta, and then we left behind the dr. Now, though, I'm not going to go ahead and be able to just see what that integral is going to be. So I'm going to have to do it in both x and y in this case. So we will call this direction, we're going to call this the y direction, and we'll call this the x direction. Okay? So probably the best way to get started with this, though, we're going to need to figure out that distance because I still need r, right? Because that's what goes into my moment of inertia definition. It still should look like mr in some way. Well, the easiest way to do this then, I'm going to have to integrate from across one side and across another side. But we're going to find it easiest if we keep some symmetry here. So if we divide this way, so here's my 0. Does it make sense that you would want your axis of rotation to be at the 0 of your coordinate system? Sure, that's going to make things a lot easier for you. And we're free to pick our coordinate system however we want. Why not pick it in such a way that it's going to be easiest for us to envision that rotation going around with this? So now I'm rotating around that central point there. Well, the only difference that makes is, let's suppose, I believe I chose A for the top part. So if this whole distance is A, and I'm starting from here, then this is going to A over 2, and this is going to negative A over 2. So instead of integrating from 0 to A, I'm just going to integrate from negative A over 2 to positive A over 2. That way I can keep my axis of rotation right on the 0 of my coordinate system. That'll make our jobs a little bit easier. All right, and then we call this side B. And so by the same token then, this would be positive B over 2, and this would be negative B over 2. So I'm going to integrate, instead of from 0 to B, I'm going to integrate from negative B over 2 to positive B over 2. Let's clean that up so we can actually read that. And so that's going to be positive B over 2. All right, so those are going to be our limits of integration. All right, the technique is the same. So we're going to find a relationship between the density and the mass. So here again, we are going to assume that A and B are both much greater than the thickness of it. So I can consider this to be an infinitely thin disk. And for the robot, for the circuit board certainly, that's probably a good bet, right? The circuit board itself is very thin compared to its width and its height. All right, so we're going to use our same expression, and so we're going to say sigma is going to equal m over A. Right? Okay, so if I'm going to solve this for m then, this tells me that m is going to equal sigma times A, just like we did before. Now I need to take the derivative of both sides so that I can get a dm, because this little piece right here, remember, is a dm. All right, so I'm going to take my dm, take the derivative of both sides, and this is going to give me a dm is equal to sigma dA. All right, and so far this is exactly what we did before. Now, what's different here now is I need to find a relationship between dA, our differential area, and our two coordinates, which in this case are x and y instead of r. Well, that shouldn't trouble you. How do I, if this is a square, how do I find the area of that rectangle? Well, dA is simply going to be dx times dy. Because if this is my little piece dm, it's got size dx by size dy. So the area is going to be dx times dy. All right. Turn over to the next page then. All right, let's copy over what we know so far. We know that sigma times our area, which is dx dy, is equal to the mass of that little piece right there. So we're just going to take this expression that we found and plug in for dm in our definition of the moment of inertia, which was the integral of di was equal to just I, which was equal to r squared, integral r squared dm. Putting that in then, we're going to get the integral of r squared sigma dx dy. Well, now I'm integrating with respect to two variables, so I need a double integral. I also need to have my limits of integration. Remember that we had centered our axis of rotation so that it was at the 0 of our coordinate system. And so we were going from minus a over 2 to plus a over 2, and from minus b over 2 to plus b over 2. Okay, so those are going to be my limits of integration here. I don't really have room to write them, but we'll kind of indicate it's minus a over 2 to plus a over 2, and then minus b over 2 to plus b over 2. Well, now I've got this factor of r in here, which definitely depends upon x and y, right? If this is the point that I'm interested in, this is r. So we need to know how that distance r there is related to x and y. And this is a very common thing that you're going to have to do. You're going to have to say, okay, I've got this r squared. I need to convert it into whatever coordinates I happen to be using into x and y and z. Well, in this case, then we only have an x and a y. So can you give me how r is related to x and y? Well, it's in the hint. That's just the Pythagorean theorem. So r is equal to the square root of x squared plus y squared. We'll plug that into right here. Fortunately, it's going to be squared, so that square root's going to go away. So I get this double integral. Remember, minus a to plus a, minus a over 2 to plus a over 2, minus b over 2 to plus b over 2. And then r squared is going to give me an x squared plus y squared dx dy. And so now I'm ready to go. I'm ready to integrate this. So remember that the dx dy is multiplied by both these terms, both the x squared and the y squared. And that's where a lot of students mess up. So don't get caught from that. Let's write it out explicitly. Let me clear out some space up here. Let's go ahead and multiply through in that parenthesis explicitly. So I have that I is equal to my double integral with my limits, x squared dx dy plus y squared dx dy. It is not x squared dx plus y squared dy. That's where people make their mistakes, all right? And so it's all of this then is integrated. So let's do the first one. Let's do y first. So I have oh, whoops, we forgot our sigma term here. Let's go ahead and pull that outside because it's constant. So this is equal to sigma, and that comes from this term right here. Okay, so I've just pulled that out. All right, so let's integrate with respect to y. So I'm still going to have from minus a over 2 to plus a over 2. Now I'm going to integrate x squared dx dy with respect to y. Well, there is no y term there. So that's going to be y x squared dx. The integral of dy is just y. Integrating this one then, I'm going to integrate my y squared, and that's going to give me a 1/3 y cubed dx. Now you could pull out that dx, but it doesn't really help you because you're going to have to multiply it right back in. Now the only thing we need to remember though is that we are evaluating this from minus b over 2 to plus b over 2. Let's go ahead and substitute in those constants so that we can get rid of all of our y's. So I is going to be the integral from minus a over 2 to plus a over 2. Substituting in for y, let's do this first term here. We just put in our plus b over 2. So I get plus b over 2 x squared dx plus, put it in here, that's going to give me a b cubed over 8. 2 cubed is 8. So that's going to be 1/3 b cubed over 8 dx. That's my first term using this. Now I need to subtract, plugging in this one, but it's going to be the same thing. It's going to be minus b over 2 x squared dx minus 1/3 b cubed over 8 dx. Make sure that you see that as we plug that in. And the minus term comes about because I have a minus b times a minus b times a minus b, and so that's going to be minus. Well, now we can already see that that minus, when it carries through, makes everything positive. So let's combine our x squareds terms, and let's combine our terms that don't have any x's at all. And so I get I is the integral from minus a over 2 to plus a over 2. b over 2x squared dx plus b over 2x squared dx is b x squared dx. Then combining these, 1 over 3 times 8 is 24. So I've got 1 over 24 b cubed dx plus 1 over 24 b cubed dx. Well, that's 2 over 24 b cubed dx, which is, this is a b, which is 1/12 b cubed dx. Let me make that b a little easier to read. It's lost in my parenthesis there. There we go. All right, so now we're ready to integrate with respect to x. And if you don't follow what we've done here, go back through, pause it, rewind, make sure that you're seeing what we're doing. All right, so I need to integrate with respect to x now. And so I get I is, this first term is going to be my x squared integrated to that is going to be a 1/3 b x cubed plus, there is no x term here, so d integral of dx is going to be x. So 1/12 b cubed times x, and that has to get integrated from minus b over 2 to plus b over 2. I'm sorry, a. Whoops, that was for y. Let's go ahead and make sure that's clear, because I'm integrating here from minus a over 2 to plus a over 2, so I have to evaluate it from minus a over 2 to plus a over 2. All right, so we're putting in for x cubed now. And so let's do this first term, and we'll keep that in brackets like we've done before. So this is going to equal 1/3 b, and then that's going to be an a cubed over 2 squared is 8, or 2 cubed is 8, plus 1/12 b cubed times a over 2. And both of those are positive. Minus, and then you should see it's going to be the same thing, just like we did before, minus 1/3 b, it's going to be a negative 1/3 b, a cubed over 8, minus 1/12 b cubed, a over 2. Okay, so let's do some combining here. And so I then is going to equal, both of these all become positive. So let's add them. I've got a 1/3 times 1/8, that's going to be 1/24. So these two gives me 1/24, but I've got two of those. You see that they're both ba cubed. So that's going to give me 2/24, which reduces to 1/12 ba cubed. And then bringing these two together, that's 12 times 2 is 24. 12 times 2 is 24. Add those together, I get 2 over 24 again. And so that's 1/12. And then I'm going to have a b cubed times a. All right, and then, whoops, we forgot we need to have our sigma out in front of all of these. Let's put that in so we don't forget. So I'm going to have all of this multiplied by sigma. Now, just like before, we are done. And if we are given sigma, then that's all we need, is we need sigma and the size of the two sides, so the length of A and the length of B, and we're good to go. But let's go ahead and put it in terms of the mass, since that's what you're normally going to find. Okay, so we know that our mass is going to equal sigma AB. Let's make sure we understand that, because I'll put it up here. The area is going to be A times B. That's the area of our board, of our main board here. That has length A and that has length B. And yes, we went from minus A over 2 to plus A over 2, but that whole length is going to be A. So that's my area, and we know that sigma is equal to my mass divided by my area. And so I can plug that in. This is what I've got. And so I can plug that in for my sigma over here, and let's see what that gives us. Since we're running out of space, we'll try to put it down here. So that gives me that I is equal to, let's put our sigma in, which is going to be m over AB. So that's going to be m over AB times 1/12 b over a cubed, or b times a cubed, plus 1/12 a b cubed. So in this first term, I'm going to lose an a. Let's just go ahead and write that out explicitly. So this is m. I'm going to multiply through by ab. And so I get 1/12. And that's going to be ab over ab. So I'm going to multiply that through. And you see that my b's cancel and one of my a's cancel, so I'm left with a squared. Here my a's cancel and one of my b's cancel, so I'm left b squared. So I have 1/12 a squared plus 1/12 b squared, and we'll do one final bit of simplification. We'll write it over here, and I then must equal 1/12 m times a squared plus b squared. And that is the moment of inertia for a thin rectangular plate rotating about its center. And you see that it still has the units that we expect. It needs to have units of kilogram meters squared, and it does. Also, do you notice that the a squared plus b squared is analogous to our radius squared? So I still basically have our mr squared, and so that 1/12 then becomes my shape factor in that case. All right, so this procedure, as you can see, there can be a lot of integrations that come into it. None of the integrations are hard, but there is a lot that you have to keep up with. Know that it will simplify a lot of things out. A lot of stuff is going to cancel out, and so if it doesn't, then you've probably done something wrong. All right, so now you know the basic principle for how to find the moment of inertia for any given object. Now, if it's an object that varies with density, or the density varies with distance, or it's some weird shape or something like that, well, there's nothing you can do. You're going to have to go back to this original technique, do the integration, and that's actually going to be pretty common. However, there is a list of common shapes on the page after this, the very last page of this lesson, that you can then use anytime you have that particular shape. Now, there's a couple of things that we can do that'll make our job easier. What if I have my disk, but I'm rotating it around this way? So it's all flipping around this kind of thing. I've got some bizarre sort of thing like that. So instead of rotating around the center, I'm rotating some displacement away from it, and we'll call that displacement h, just for grins and giggles. We need some sort of symbol for that. All right. So this is called the parallel axis theorem. What that means is, if I know the moment of inertia about the center, let's do that in red. So if I know the moment of inertia about this center, and you just look that up on the next page, then I can add the mass times how far away I am from that center, and that will give me my new moment of inertia. Now, there is a trick to this. They do have to be parallel. You can't have them one going one direction and one going another, or even some sort of weird angle with that. They actually do have to be parallel, or this won't work. So, for example, in this case, if I want to find the moment of inertia about this area, we start off with the moment of inertia that we had before. We said that IC is going to be 1/2 mr squared, where r is going to be the radius of the disk. But then I, in this case, is actually going to change. The mass didn't change, the object didn't change. But remember, it matters where you rotate around. So this is going to equal to 1/2 mr squared plus m times h squared. And it really is as easy as that. So you can take pretty much any kind of thing that you want to deal with, move it away from the axis, and then use this theorem right here to get what you need. The last piece then is here, and that's that the total moment of inertia is equal to the sum of its parts. So let's suppose that, and we're going to do this in the next lesson, let's suppose that I've got a figure skater who has their arms out like this, and we'll say that that's their feet, and their feet are very close together. Okay, so I could do this as by finding the moment of inertia of the figure skater's head. We'll idealize that as a circle. Maybe I've got a cylinder here rotating around the center, and then we'll consider these two to be a single cylinder rotating around that way. So all three of these, I can find the moment of inertia for this, this, and this just by looking them up, because they're all rotating around the center. Now here, though, I have another sphere, but instead of rotating around its middle, it's rotating some distance h away. You see how that's all going around this way? So I just take I look up my same value for my sphere, but then I add that plus mh squared. Same thing over here. I've got another sphere, and then I'm going to add an mh squared. The total moment of inertia then for this figure skater then is the sum of all 5 of those parts. 1, 2, 3, 4, and 5. Really is as easy as that. So we can get a fairly decent model of a robot simply by breaking it down into these fundamental shapes. And yeah, if I might treat my distance sensor as a rectangle. It's obviously not, because I've got these circular pieces here, right? From where it's going. But even just ignoring the circular pieces and just treating it as a simple rectangle is going to give me a pretty good idea of how this thing is going to rotate. And then if I need to refine it more, then yes, I can actually work it out using these smaller pieces and add up everything until I've got what I finally need. So those are all the techniques that you're going to be using anytime that you're trying to find the moment of inertia. So you see that finding the moment of inertia of an object is often non-trivial. And a lot of times what we'll do, like we said, is we'll break the object into pieces, and then we'll put those pieces together and use the parallel axis theorem if they're not actually rotating around the center of the object, the main object from here. Also, a lot of software packages you'll be able to put in a 3D object, and it can calculate the moment of inertia for you by doing a numerical integration, taking little pieces and calculating the moment of inertia of each tiny little piece, and then adding all those up. And so that's going to be the way in the real world that you're often going to find that moment of inertia. But in order for you to understand how that software package is doing it, you got to understand how to do the calculation in the first place. So that's what we've done here. From here on out, you're really just going to need to look up the values from that table there. So those values in the table in your book, it's probably a good idea to copy those into your flipbook so that you've got those available on the exam. You're not going to have time to actually do this whole integration for that. As you saw, it takes a long time to actually do. But we do expect you to be able to use the moment of inertia. And so that's what we're going to be building with in the next couple of lessons. We'll see you then.